All right, so let's look at buffers and solving calculations with buffers using something called the Henderson-Hasselbalch equation. So we just did an example of a buffer calculation using an equilibrium table. We were able to solve for the pH by solving for the initial concentrations to go in our equilibrium table and solve for the pH. So you can always use this approach to solve these problems. I'm going to show you another approach. So this is the Henderson-Hasselbalch equation, and the Henderson-Hasselbalch equation says that the pH equals the pKa plus the log of the concentration of base over acid. So that's the Henderson-Hasselbalch equation. If you were to Google the Henderson-Hasselbalch equation, you may see it written in a different way, where it would say the pH equals the pKa minus the log of acid over base. That will also give you the same answer mathematically. This is the version that your textbook uses. This is the only version you need to know. This is the version that I will use. I just wanted you to know that if you were to see this in some other resource written another way, the math does work out the same, and you're welcome to use whichever version you want, but this is the version that I'm going to use. So let's walk through this. So usually you're being asked to solve for the pH. Remember what the pKa is. pKa is the negative log of the Ka. So remember, the Ka is the acid ionization constant for the weak acid, plus the log of this ratio, base to acid. So remember, base, this is the conjugate base, the A minus, and acid, this is the weak acid, HA. So these would be the concentrations of this buffer system. So you could say the concentration, the initial concentration of the conjugate base and the initial concentration of the weak acid. So remember, this little zero down at the bottom means initial. So let's use this formula for the problem that we did, the example that we just did using an equilibrium table. So we would still need to do step one, find the initial concentrations of the weak acid and the conjugate base, because that's what needs to go here. And this problem did not give us the initial concentrations, it gave us the concentrations before they were mixed together. This is another thing to pay attention to, because some problems will say these are the initial concentrations, and then you wouldn't need to do any dilution calculations. Here, we needed to do a dilution calculation. We already did this in the previous example, so I'm not gonna write this out again. But in the previous example, we saw that the initial concentration, I'm just going to put that little zero there to remind us, this is the initial concentration in our equilibrium table, not the final concentration. The initial concentration of our weak acid we calculated to be 0.0050 molar, and the initial concentration of the weak base, the conjugate base, we calculated to be 0.045 molar. So now once we have these, that's where that's going to go, and we're also given the Ka in this problem that we did before. The Ka was 6.3 times 10 to the negative 5. So pKa is the negative log of the Ka, 6.3 times 10 to the negative 5. Let's see what that is. 4.20. So remember, anytime you're taking a log, the number of significant figures and the value that they took the log of is the number of decimal places in your log. So the pKa is going to be 4.20 in this problem. So now I have everything I need to solve for the pH. So I'm going to say pH equals the pKa, 4.20, plus the log of the concentration of the base, which is A minus, 0.045 molar, over the concentration of the acid, 0.0050 molar. You could write molar here. These are just going to cancel. So now we're going to solve. So I'm going to say, you could do this all in one step, or you can do it in multiple steps. I'm going to say 4.20 plus the log of 0.045 divided by 0.0050 equals 5.154, whatever. It should have 2 decimal places because this is a pH. pH equals 5.15. This is the same thing that we got when we used the equilibrium table. We got a pH of 5.15. Here we used the Henderson-Hasselbalch equation, and we also got a pH of 5.15. So this can always be used to solve for pH of a buffer. You also can always use an equilibrium table. I will never tell you which way to solve a problem on an exam. As long as you showed your work, whichever way you chose to solve it, that would be totally fine. This is a big shortcut in terms of writing out work and calculations. This is only for buffers. Remember, buffers have a weak acid and its conjugate base. You would still need to do the dilution calculation that we did in this previous example, but once you know the concentrations and you've solved for the pKa, it's just a much less complicated way of solving the same problem. So here is the same buffer example as the previous video, but just using the Henderson-Hasselbalch equation.